This is section 10.8, systems of nonlinear equations. So this is a situation where you don't just have variables of degree 1. And we can see that we have an example here. We have x squared plus y squared equals 40, and we have y equals x plus 4. And our job is to find out the values of x and y that make both of those equations true at the same time. What you want to try to get good at is identifying what you have. So in this situation, we have x squared plus y squared equals 40. We want to recognize that this is the equation of a circle. And when we see y equals x plus 4, we want to notice that that's the equation of a line. So being able to understand that can give you an idea of what you're dealing with. And then I do have the picture for you already over on this side, so you can see that we are trying to find out the intersection points here, x comma y, for where the circle and the line meet. We can see visually where those are, which is helpful. So you can actually see just by graphing them what the solutions are going to be, but we are going to do it algebraically as well. So we have equation number 1 here, and we have equation number 2, and we're still following the same idea. We can use substitution, we could use elimination. Either one will give us, in the end, the correct answer. So with this one, substitution works well, and that's because we have one of the equations already solved for one variable. So the fact that we have what y is equal to tells us that it would be pretty simple to take equation 2 and substitute it in to equation 1. And then that would make equation 1 one variable, and then we could solve for that variable. So that's what we're going to do. So when we take equation 2 and put it into equation 1, it will look like this, except that instead of y in equation 1, I am putting equation 2, what y is equal to. But notice a lot of similarities with the other work that we've done, where you are just dealing with something that's not only linear. So in this case, we have one linear, one nonlinear. So what we need to do now is solve for x, but we have x plus 4 squared, so you want to multiply that out. You want to then see what you're left with. So we have x squared, we'll have x squared, we will have 8x plus 16. You do want to work to try and do that in your head. And then the best thing to do here, you'll have a quadratic. So you should see that you have a quadratic equation. And if we bring the 40 over, it looks like we'll have a minus 24, 0. Now, a couple things you can do here, but what you should see, you have a quadratic. You can complete the square. You can use the quadratic formula. You can factor. Obviously, we typically start with the attempt to factor, but I do want to factor out my greatest common factor first. So do not forget that piece. That is really huge. If you can factor out a greatest common factor, do it. It does not affect your solution at all, meaning that we just have this. The solutions to this are the same as the solutions to this, because the 2 doesn't matter, doesn't change any of the solutions. So now, let's see if it factors. Go ahead and try that out. Factors of 12, but we want the difference to be a positive 4. Okay. So you can see that that's giving us 2 solutions, x equals 2, x equals negative 6. Not too surprising. Here's, x being 2, x being negative 6, and you can see that that is the x value for the graphically speaking. Now we do need y, but we know that y equals x plus 4. That's equation number 2. So we quickly are able to get y by doing 2 plus 4. Over here, y will be negative 6 plus 4. I should just do that out in a couple steps for you. So x, negative 6 plus 4. So we end up with 6, and we end up with negative 2. So our solution here, there are 2 solutions, 2 things that make this true, so do notice that. We have 2 comma 6, and we have -6, -2. So those are our two solutions to this nonlinear equation. Notice again, make a note, we used substitution in order to find our answers, our solutions. So this is just going to tell you that there are two ways you can use substitution. Sometimes it may be helpful to use elimination. You have some options here, but just notice that both of them are possible, and you have to kind of discern which one might be better for you. Like this one. So notice that in this example, we have, as you can see, two equations of two variables, but neither one is linear. And in fact, over time, you hopefully will be able to recognize that the first one is actually an example of a hyperbola. That's what you see here. And the second one is an example of an ellipse, and that's what you see here. You should also maybe notice that we have 4 intersection points here, and none of them look particularly easy to find. So if you're to be using something like Desmos, you could obviously graph these and you could find out the points of intersection. But in order to do this algebraically, we don't do it graphically, but we can see at least that these points are not going to be nice integers like we saw in the last one. Not that sometimes they aren't, but in this example, they won't be. So in this case, I'm going to use elimination. And the reason I want to do that is because when I think about this, solving one of these equations for x or y is going to be kind of challenging. I can do it, but it's going to give me a plus or minus square root. If you kind of think about what that would look like to solve. So I don't want to deal with that. I would rather solve this by elimination. So let's label our equations here. And then you have a couple options, but I'm going to take equation number 1. Maybe I'll write just a little bit more so you can see what I'm doing here, but I'm going to take equation 1 and I'm going to add it to equation 2 that's been multiplied by -4. So equation 1 plus -4 times equation 2. So it's going to look like this. And that's the end game here. So I have 4x squared minus y squared equals 16. My second one will now be -4x squared minus 64y squared equals -64. So a lot happening there. Then using the elimination method, we just add. And what that will do, of course, is rid ourselves of our x squareds. We'll be left with -65y squared. And over on the other side, it looks like we will have -48. Now, you can probably tell pretty quickly what we already knew, which is that these are not, we have a fraction here. And so we have 48 over 65, and then, oh no, when we take the square root of both sides in order to solve this for y, we get plus or minus the square root of 48 over 65. And that is not pretty, but that's okay. I'm going to leave it as it is here. So notice that's 2 different y values. We have 2 different y values there, a positive square root 48 over 65 and a negative square root 48 over 65. Those are the 2 y values that you see in the picture. In order to solve for x, let's see, I'll come here. So in order to solve for x, so this is kind of like, I know I got a lot of 1s and 2s here, but that's 1, that's 2. So in order to solve for x, I can use either equation. So I will use my top equation. I will put 4x squared minus, and then my y squared, I'm going to put in, I just want you to see that you can put in plus, or you can put in the positive or the negative square root 48 over 65. It doesn't matter because when it's squared, it's going to be the same. So, if If I have plus or minus here, it doesn't matter. It gets squared anyway. So it doesn't affect things. If it did affect things, I'd have to do each one separately. But I don't have to because they're the same. You know what? I'm just going to leave that because they are the same. Over on the other side, I have my 16. Okay. So, you know, again, this is not pretty, but not everything is. So, however, when I take plus or minus the square root of 48 over 65, I square it, square root squaring, I get 48 over 65. So at least I have that, 48 over 65. And then we're just solving now for x. That's our goal here. So, you know, some stuff will happen. 48 over 65, and then 16. And then I want to add that. So 4x squared equals, I'm going to take 16, I'm going to add it to 48 over 65. You know, common denominator is going to be a 65 there. So you end up with 1088 over 65. Adding those two things together. And then I will divide by 4. Dividing by 4 is the same as multiplying by 1/4, so that will give me 272 over 65. Okay, and then we have to take the square root again, so plus or minus the square root of 272 over 65. So what you want to see now is that we have two y values, we have two x values. Whether we put in the positive y value or the negative y value, it's going to give us both x values. So what that tells us is that there are 4 solutions. It's every possible combination. So let me just write the word solutions here since these are not quite as maybe pretty as some of the other things we've had. So what I'm saying is, I don't know how big to make these. What I'm saying is we have 4 solutions. 4 solutions. We have 2 solutions with the positive 2 square root 272 over 65. So I have square root 272 over 65, square root 272 over 65. All of that is in the square root. But then I have 2 with the negative square root 272 over 65. And negative square root 272 over 65. That's because there's 2 possible y values for every possible x value. So we have positive, positive. Now I'm doing the y values here. Positive, positive. I also have positive, negative. Okay. And these are just numbers. I mean, you could find out what these are. Maybe I'll do that real quick and you can kind of see a decimal equivalent here. That might be helpful. On the other side with the negative x values, you have the positive y value and you have the negative y value. So notice in our picture, we do have one from each quadrant. So it's not surprising that we have both positive x and y's, both negative x and y's, and then alternate positive, negative, negative, positive. So I just put these into my calculator and we can see that x is about, just putting the square root of 272 over 65, we get a plus or minus 2.05. For the y values, I do plus or minus the square root of 48 over 65, and I get plus or minus 0.86. So 0.86. And then if we take a look at our picture here, we are not too surprised to see, I already have an arrow, I'll just do another one here. You can see that for this solution that we have right here again, you can see that the x value is, you know, a negative 2.05 makes sense, and then the y not quite being positive 1, that's one of our solutions. And that would be, it looks like, that solution there is, for example, this solution here, a negative x value, positive y value. We also have this solution right here. You see that it has the same x value, that negative 2.05, just a little bit less than negative 2, but not quite a negative 1. So that, as you can imagine, is our negative negative. So the four values that we have do relate, of course, to the 4 points that you see on the visual representation of the intersection of this hyperbola with this ellipse. But algebraically speaking, it was best to use elimination. So if you want to make a note, what we did here was use elimination to solve this one. Elimination. We eliminated the x, solved for y, and then back substituted to get our x values. And that is section 10.8.